Welcome to MMA, your Mixed Model Academy. In this series of tutorial videos, we're going to learn how to specify mixed effects models with complex variance structures in MMA. MMA's mixed model form offers a wide range of variance structures, enabling us to define a simple to a very complex variance structure for each random term in our model, including the residual. In this video, we're going to learn how to model the correlation structure of repeated measures data. Mixed effects models provide a powerful tool for modeling temporally correlated data. The goal of correlation modeling is to describe how the lack of independence between measurements changes as the separation in time between them increases. For example, if we measure a patient's blood pressure in January and again in February, we would expect these two measurements to be more alike than two taken in January and July. MMA offers several choices of correlation structure. The simple correlation structure, CORE, also known as uniform correlation, assumes that the correlation between measurements is constant, regardless of how far apart in time they are. The autoregressive model of order 1, AR1, allows the correlations between measurements to decrease as the length of time between them increases. This is a more realistic correlation structure for most repeated measures datasets than assuming constant correlation between all pairs of measurements. The most flexible correlation structure is the general correlation structure, CORE-G. It allows a separate correlation for every pair of measurements. The general correlation structure can be used for repeated measures data at either equally or unequally spaced time intervals, whereas the autoregressive correlation structure should only be fitted to equally spaced measurements. Finally, the MMA form also offers the identity structure. This assumes that observations are uncorrelated or independent of one another. Let's look at an example. The example we'll use is a repeated measures dataset on the orthodontic growth rate of children. You can download the data from the global project Orthodontic Growth Data. In this study, researchers at the University of North Carolina Dental School tracked the orthodontic growth of 27 children every 2 years from the ages of 8 to 14 years. They did this by measuring the distance from the center of the pituitary to the pterygomaxillary fissure, 2 points that can be easily identified from X-rays on the side of the face. We're interested in modeling the response variable distance in terms of sex and age. Age C is age centered at 11 years, i.e. age minus 11, and age F is age defined as a factor. There are several reasons why covariates are usually centered: to improve interpretability of the model, to reduce the correlation between an interaction or polynomial term and its component terms, for computational advantages. The data set contains 3 variates: distance, which is the response variable, age, and age C. It also contains 3 factors: subject, the individual children whose measurements were taken, sex, and age F. Let's model the distance data, allowing male and female children to have different growth patterns as they age. I've partially filled in the model already. As this is repeated measures data, we must take into account the correlated nature of the distance measurements taken on the same child as they age. For this study, distance measurements taken on the same child at consecutive ages should be correlated, but measurements on different children are assumed to be independent. This correlation structure is imposed by specifying the appropriate variance structures on the residual, which for this dataset corresponds to the combination of the factors subject and age F. The orthodontic growth dataset contains a total of 108 observations from 27 children, the subject factor, each measured 4 times at ages 8, 10, 12 and 14, factor age F. Since the subject by age F term is equivalent to the residual, we'll put this term into the residual field. We set the variance structure associated with the subject term to ID, since the distance measurements taken on different children are assumed to be independent. Then, because the distance measurements taken on the same child over consecutive ages should be correlated, we select a correlation structure for the age F term. This corresponds to an I crossed with C covariance structure, where the identity matrix I corresponds to the independent children, and the covariance matrix C corresponds to the correlated measurements over age within a child. Recall that AR1 is the autoregressive correlation structure of order 1. This allows the correlation between distance measurements taken on the same child to decrease as the time between the measurements increases. Core is the simple correlation structure, which assumes that the correlation between distance measurements taken on the same child is constant, regardless of how far apart in time the measurements were taken. And Core G is the general correlation structure, which allows a separate correlation for every pair of ages. For this example, let's model the distance data using a repeated measures model with a general correlation structure. What we're saying is that the residuals between different children are independent, but the residuals originating from measurements taken on the same child but at different levels of age F are correlated based on the Core G correlation structure. Now that our repeated measures model is clearly defined, we can click Generate to produce executable code. Thanks for watching Part 1. In Part 2, we'll learn how to model this repeated measures dataset using random coefficient regression. And in Part 3, we show how to model spatially correlated data from an agricultural field trial. If you have any questions, please contact support at mixedmodel.academy.